Hello. So today we're going to be talking about currents in a magnetic field and what happens to them. So the first thing we need to know is that there'll be a field interaction when a current interacts with a permanent magnet, and this is going to induce a force. We call this force the motor effect. And this is going to be quite important. So to kind of explain how this works, let's say we have a permanent magnet right over here. We have a north and we have our south pole, and we're going to draw our magnetic field between them. Obviously, we know our direction always goes from north to south, and we have our magnet. But let's say we want to put in a current inside this magnetic field. Let's say we have a current over here. What's going to happen is actually this current is going to feel a force on it, and it's going to either move up or down depending on the magnetic field and the current. And so we can find the direction of this force using the right hand slap rule or Fleming's left hand rule. I personally prefer the right hand slap rule, but I will explain both. So when we're trying to use the right hand slap rule, we're going to be using this over here. This is a right hand slap rule. And so you're going to be putting your palm out in front of you. Your four fingers are going to be representing the magnetic field or the direction of the magnetic field. And your thumb is going to be representing the current. So when we do that, let's use this situation. For example, the one we used over here. Our four fingers are going to be pointing to the left, and our thumb is going to be pointing. Let's say that this current is actually coming towards us. If this current is coming towards us, then we know that the current is going to experience an upward force because our palm is going to represent our force, and that is going to be pointing upwards. However, we can also use this rule for thinking if this current is going towards the paper, then actually it's going to be experiencing a downward force. I find that the right hand rule or the right hand slap rule is a little bit easier to remember because the force is kind of, makes sense. You slap it, you have a force, and your fingers also line up with the direction of the field, and I think that's quite useful. Thumb you can remember as current, and the thumb will also correspond with the right hand grip rule where you're using your thumb for the direction of current as well. However, there is another option you can use if this is a bit, you don't quite like the right hand slap rule. And this is, I think, a bit more common, which is Fleming's left hand rule. Our thumb is going to be representing the force. Our index finger is going to be representing the magnetic field or the direction of the magnetic field, and your middle finger is going to be representing current. And this is good because it can also help visualize that all of these things or our directions are perpendicular to each other. And so we can align these three components with our graph again, and we're going to be getting the same result that basically if the current is coming towards you, our force is going to be up. If the current is going towards the screen or away from you, then our force is actually going to be down. And the easiest way to remember this, because you'll have to remember that the force, direction of magnetic field, and current have to align with these specific fingers, is what I was taught is using FMC, father, mother, and child, in that order. It's quite easy to remember it that way. So this is another option to remember motor effect. So let's talk. We've been talking about like a single current, a wire kind of, that's perpendicular to the magnetic field. But let's think about the whole wire for context. So let's go wire in a magnetic field. So let's say we have our magnetic field, or let's make it red to line up with before. We have our magnetic field going in this direction. And we have a wire going over here. So how are we going to find out what this force is, right? Well, luckily there is an equation we can use for this, and it's going to be, let me write it down here first, this. And so this isn't going to make a lot of sense right now, but we're going to try and explain it. So B over here is our magnetic flux density. And this is just one of the properties of the magnetic field that you'll either be asked to calculate or be given. So it's just one of the properties that we need to find the force. I, we should be familiar with, is going to be our current. Specifically, you're talking about our conventional current flow. So we have our current. L is going to be the length of the wire in the magnetic field. So it's going to be, this length. Or if we had another wire that was like this, and only this bit was in, only this part of the wire was in the magnetic field, then that would be the length of the wire in the field. So length is dependent on that. And then we have our angle theta over here. And so our theta is actually going to be the angle between the current and the magnetic field. And so we're actually talking about this theta, or this angle over here. And using that, we can actually calculate what the force on this wire is going to be due to the electric field. So this is going to be all for now. Hope you understand.